So here is a motivating question for my subject that will lead us through several videos in a row. How many necklaces can you make with 2 red beads, 2 blue beads, and 2 black beads? And so note, the point is that in general, you might say that it should be, if you've had a combinatorics class, you might say the answer should be 6 choose 2 times 4 choose 2. You choose 6 of the places to put the red beads, and then 4 of the remaining places to put the 2 beads. But that's not correct because, well, if I take a necklace and I rotate everything clockwise by 1, that's still the same necklace. Likewise, if I take it and I flip across this horizontal axis, I still get the same necklace. So this formula would be overcounting because it would count each of these as separate necklaces. And so we need a different formula to solve this problem. And it turns out the answer involves group theory. And it's worth pointing out, way back at the beginning of the course, I did emphasize that there was an application to chemistry here. If you're interested in counting the number of distinct molecules with the same number of atoms, carbon atoms, hydrogen atoms, and oxygen atoms, you usually end up having to use group theory and group actions, which is the theory we're getting into next. As another application that would make an interesting math project for Math 4390, for those who haven't taken that course yet, you can ask how many tetrachords there are, which is a music theory question, where a tetrachord is 4 musical notes. But of course, 2 tetrachords are considered equivalent if they differ by changing the key. And using group theory, you can calculate exactly how many there are and list them. So what is this underlying mathematical structure behind all these examples? It's a group action. So group action of a group G on a set X is a function f from G times x to x. So we will usually, instead of writing f of gx, we will usually write g dot x. And it has to satisfy the following 2 requirements in order to be a group action. 1, for every 2 elements in the group, and every element in X, must be the case that when you act by G prime on X, and then act by G on the result, you get the same thing as when you act on X with the product of G and G prime. Second is that for all elements in X, E dot X is the identity element. So the first natural example that you've actually seen in previous courses would be when G is the set of real numbers, non-zero real numbers under multiplication, and X is literally any vector space. Then what is the group action? You act on a vector by scaling each coordinate by the same constant. And the fact that it satisfies these 2 properties are actually 2 of the axioms in the definition of a vector space. So a group action is sort of a generalization of the notion of scalar multiplication. The only difference now is that your scalars are a group instead of elements in some field. And your vectors are just a set, so you don't have vector addition anymore. You just forget about that. You just have scaling axioms. So let's start with our first real example. We'll let G be the modular group of integers mod n, and we'll let x be the integers 0 through n minus 1. And G will act in the way one might expect. G on I is G plus I mod n. In fact, this is a more general example. You can always take any group G and let x be equal to G itself, with the action just being ordinary multiplication. Then condition 1 is the associative law for the group. And condition 2 is the fact that you have an identity element. So every group acts on itself. And so that gives a proof for this case, because this is just this special example. X can also be viewed as the integers 0 through n mod n. As a third example, let G be the dihedral group. Let x be the integers 0 to n minus 1. Here we're viewing these as mod n for these definitions. We're going to let G act on x as follows. Given one of these rotation operations and an element x, r to the I dot x is going to be x plus I mod n. And r to the I times s, these are the other elements, these are reflections. It's going to act on x by sending x to negative x plus I mod n. Under our standard labeling of a polygon, you label it counterclockwise, then literally if you look at vertex x, then this is actually just sending you to what happens after you rotate I times. You end up at x plus I mod n. And similarly, ignoring the I right now, S is the negation operation. It's this horizontal reflection through the axis of reflection that goes through 0. It sends 1 to negative 1, which is n minus 1 mod n, 2 to negative 2, which is n minus 2 mod n, and so on. And so these formulas are really just telling you where the vertices on the polygon go in the normal group, in the normal symmetries. But we need to actually prove that that's a group action, so let's do the proof. So we need to check, let's check the second condition first because it's easier. E dot x, well that's r to the 0 dot x. That's x plus 0 mod n. Well, that is definitely just x. So really the hard part is the first case. We need to show that for any G prime in the dihedral group, that we're going to have this equality. Well, it looks like it's going to break into cases based on whether or not these elements are rotations or reflections. Alright, so here's the first case. Suppose G and G prime are both rotations. Then we replace the G's with the corresponding powers of R. r to the j dot x is x plus j mod n. R to the I applied to x plus j is x plus j plus I. Addition is associative. Addition is commutative. So we get x plus I plus j. But that's what you get when you apply r to the I plus j, which is g times g prime. So we do in fact get that acting on g prime, and then g is the same as acting on by their product. On the other hand, suppose g prime is r to the j times s, and I just add s's where I need to. Recognize that that means I need to have a negative x. The negative x carries through until this point, and then you get r to the I plus j s times x. And that's what you need for case 2. In the third case, let's look at both reflections. The only difference that changes now is when I act on the outer reflection, I have to negate everything inside, and so negative x plus j becomes positive x minus j. And so down here I have I minus j being added to positive x. So that's what happens when I act by r to the I minus j. And r to the I minus j is what you get when you multiply these two reflections together. Finally, you can check in the fourth and remaining case that if the outer group element is a reflection and the inner group element is a reflection, you do in fact get that acting by rotation, and then reflection is the same thing as acting by their product. Hence, the dihedral group does in fact act on 0 to n minus 1. As another example, the symmetric group of all permutations acts on the set 1 to n. So here's the way the group action works. Given an integer, positive integer I in this set, and a permutation sigma, sigma dot I is just sigma of I. So for example, if sigma were the permutation 1, 2, 3, 4, 5, 6, 4, 5, then sigma dot 1 is 2, sigma dot 3 is 1, sigma dot 4 is 5. So let's check that this is in fact a group action given two permutations, sigma and tau. Sigma dot tau dot I, by definition of the group action, is sigma dot tau of I. By the definition of the group action again, that is sigma of tau of I. But this is the definition of function composition. And function composition is our group operation for the symmetric group. And so we have the group operation for the symmetric group, and we have this is the definition of our group action again. Sigma times tau dot I is by definition sigma composed of tau of I. The other condition we have to check is that E times I is I. But what is E? For the symmetric group, it's the identity permutation. So that tells us that it does have the property we want it to have. Thus, the symmetric group acts on integers 1 through n.